Hello everyone. In this video we will discuss full header. So a full header takes three inputs, two data bits and one carry in. So here A and B are two inputs which needs to be added, and C in is carry in from previous bits, and produces two outputs. One is sum, can be represented with S or sigma, and carry out. So in this video, let's look at um, on its function table, Boolean expression and its logic circuit. So here is function table of a full adder. There are three inputs, A, B and carry in, and two outputs just like half adder, sum and carry out. So for three inputs, there are 8 possible combinations from 000 to 111. So let's see how this table is populated. So in first row, 0 plus 0 plus 0, for that sum is 0 and carry is also 0. For second row, 0 plus 0 plus 1, sum is 1 and carry is 0. So let's see, for this row, 0 plus 1 plus 1, it's 2. For this case, binary representation of 2 is 1 0. So sum is 0 and carry is 1. For next case or next row, 0 plus 1 plus 0 plus 0, sum is 0 and sum is 1 and carry is 0. So let's see the last row. It's 1 plus 1 plus 1, which is 3, and binary 3 is equal to 1 1. So sum is 1 and carry is also 1. So to implement the functionality of sum and carry, we need to find out the Boolean expressions for both functions. So now let's see how to find out their Boolean expressions. So for sum, there are 4 ones in the row, which correspond to 4 different main terms in the table. So for sum, let's say S is equal to, so we will use min term, so that would be sum of products. So the first one is 0 0 1, means A complement, B complement and C, A complement, B complement and C, plus second one is 0 1 0, means A complement, B, C complement, plus third one is 1 0 0, A, B complement, C complement, plus the last one is 1 plus 1 plus 1. So that is A, B and C. So this is the Boolean expression. This is not in a simplified form. To implement a Boolean, to implement a circuit, we need to simplify our expressions. So let's find the expression for carry, then we'll find out how to simplify this expression. So for carry, we'll use this space. C is equal to, in carry, there are 4 ones in the table again. For first one, there is 0 1 1, so means A complement, B and C, plus 1 0 1, A, B complement, C. Next is 1 1 0, A, B, C complement, and last one is 1 1 1, means A, B and C. So now let's see how to simplify these expressions. So for sum, we have found A complement, B complement, C, plus A complement, B, C complement, and so on. So there are 4 min terms. To simplify, let's take first 2 terms. A complement is common, so the remaining thing is B complement C plus BC complement, and for other two terms, A is a common term, so remaining is B complement C complement plus BC. So here the first term A complement remains same, B complement C plus BC complement is equal to B exclusive RC or B XOR C, and same case with the other one. In here B complement C complement plus BC is equal to B X NOR C, or we can write it like B XOR C with whole complement. So to further simplify it, let's consider this whole term as B. So in here, B XOR C is simply B, and here B XOR C whole complement is just like B complement. So the term will become A complement B plus A B complement, which is again equal to A XOR B. So here B can be A XOR B. So overall, we can write it A XOR B, and this B can further be converted into B XOR C, and whole expression can be simplified as A XOR B XOR C. So this is the simplified expression for sum. Now let's see how to calculate simplified expression for carry. So same, four ones, four min terms. From first two terms, C is a common variable. So A complement B plus AB complement. And from last two terms, AB is a common term. So C complement plus C. So here again, A complement B plus AB complement is equal to A XOR B, and for the last one we know that C complement plus C is equal to 1, so only A and B remains. So this is the optimal expression for carry or carry out. So we can design a circuit by using these expressions. So for sum, we see that there are two exclusive OR gates. So here is sum RS. So it takes inputs A and B, and the first gate calculates A XOR B, then second one computes its result and uses C as an argument or input for that exclusive OR and computes sum or S. For carry, there are two AND gates. So let's say first A and B. So this AND gate computes A and B, and other one computes C and A exclusive OR B. So A XOR B comes from this branch and C comes from this branch, and it computes C and A XOR B. And finally, for this OR gate, it implements an OR gate and C out is computed. So this is a simple circuit, uses few logic gates. So if we put it in a box, it will become a full adder which takes three inputs A, B and C and produces two outputs, sum and carry out. So full adder can be implemented by using two half adders. So if two half adders are attached like here, as shown by the picture, we can achieve the functionality of a full adder. So for first half adder, the inputs are A and B. It adds A and B and produces sum of A and B and a carry out, but the carry in goes as input to the second input of second half adder, and the sum of first half adder to the first input of second half adder, and C out of the first adder is ORed with the C out of the second half adder. So here we achieve sum and carry out just like a full adder. So again we can put it in a box and it will work like just like full adder. So if we have circuits for half adders, we can achieve the functionality of a full adder as well. So here full adder computes only 2 bits and produces sum and carry. But if we want to implement an adder which can add numbers with multiple bits, so for that case, we attach different adders in parallel and compute the addition. So this kind of adder is also called a ripple carry adder. For example, if we want to add 4-bit numbers, two 4-bit binary numbers like 0 1 1 0 1 0 1 1. So for this case, we need to attach a full adder for each bit. So for first addition, a full adder, for second one, for third one, and then for fourth one. In this diagram, this is a 4-bit parallel adder, it also called ripple carry adder. So it takes A0 and B0 like least significant bit, the first one, least significant bits, then A1, B1, the second ones, then A2, B2, third ones, and B3 and A3, the fourth one. And final is the C out. And here see, the first carry in is 0, because whenever we add least significant bits, whether they are 0 0 or 1 0 or 1 1, the carry in is always 0, and S0 is the sum of first bit or least significant bit, and the carry out, the most important thing in the ripple carry adder, carry out is going as input to the next full adder. So again, A1 plus B1, the sum is S1, and C out goes as input or C in to the next full adder. It produces S2 by adding A2 and B2, and C out again goes as C in to the next full adder, and it adds A3 and B3. The sum is S3, and final carry out is C out. So the carries move like waves of water, so that's why they are called ripple carry adder. So let's say if we number them, this is adder 0, adder 1, adder 2, and adder 3. Adder 0 performs the additions right away because it knows all of its inputs, A0, B0, and 0 as C in. So it computes S0, and the C out is out is attached with C in of adder 1. So adder 1 waits until the C out from the adder 0 is computed. When the carry is computed, adder 1 starts working and adds these 3 bits and produces S1, and the carry out again goes to the next adder, and next adder waits until the carry out from previous adder is computed, and same case with third adder. So in this scenario, we can attach multiple adders. Like if we want to add 32-bit numbers, so we will need to add 32 full adders in this manner so that they are dependent on each other. So next adder is dependent on the previous one, and the previous one is dependent on its previous one up to the first one. So it adds numbers, but the thing is it takes a lot of times. The next adders wait for carry from previous adder. So for carry propagation, we have just discussed carry ripple adder or ripple carry adder. It's a simplified circuit. We just need to repeat the adders for all higher bits from least significant to most significant bit, but it takes more time. So as we increase adders or bits, it takes more time and adds more waiting time for carries. Next bit addition waits for the carry from the previous bit additions. The solution is look ahead carry circuits. So that we can predict the carry. So the solution is to save the time, we just add few more gates. So our circuit could be little more complicated, but we can save the time. So in the next video, we will discuss how look ahead carry circuits work and how they save the time. So that's it. Thank you.